In this video, we're going to wrap up our discussion of Java by taking a look at a couple of additional topics and how they are integrated into the language design. Consistent with Java's dynamic nature, Java allows classes to be loaded at runtime. What this means that you can actually add functionality to a executing Java program, so while it's running, by loading a new class. And this creates potential issues with type safety and security. Because now there is a distinction between compile time and load time. So type checking of the source takes place at compile time, and this is the kind of type checking that we discussed in earlier videos. But the loader, when you actually go to load a class, you're loading bytecode. You're not loading source, and it's not being type checked again. And it could be that this bytecode didn't come from a trusted source. This bytecode might not be the output of a compiler that did type checking before it produced the bytecode. So the bytecode might not actually satisfy the type assumptions of the Java implementation. So essentially, we have to check the bytecode again, and a procedure called bytecode verification takes place when the class is loaded. All right. And bytecode verification is really type checking of bytecode. That's essentially what it does. The procedure is a little bit different because we don't have the code here is much lower level, and so the algorithms look a little bit different. But what they're really doing is type checking the bytecode. So now the loading policies are handled by something called a class loader, and the class loader is a special class in Java. And it decides what classes can be loaded. And actually early on in Java, a bunch of security problems were discovered where an attacker could get control of the class loader, install its own class loader that would be much more permissive than the Java standard class loader and subvert the system. But those issues were fixed quite a while ago. All right. And another interesting thing about Java is that the classes may also be unloaded. So you can not only load classes, you can also unload classes. And the last time I checked, this was not particularly well specified in the definition. So it was a little bit unclear exactly what it meant when you unloaded a class and what happened to all the existing objects, for example, of that class. Now I'd like to spend a few minutes talking about initialization in Java, which is quite complex. And this shouldn't be too much of a surprise because if you remember, initialization in Cool was also pretty complex. And Java is just a superset of Cool. So it has all the initialization issues that Cool has, plus much more. And now the main source of complication is concurrency, but other language features also add to the complexity of initialization in Java. And in fact, you could do worse if you want to understand a new object-oriented language than study how it does object initialization and class initialization. Because essentially what happens in initialization is that all the features of the language are going to be interacting, and you have to explain what all those interactions are and how they're sorted out in order to have a well-defined initialization procedure. All right, so now let's talk about class initialization. We won't talk about object initialization. We'll just talk about initializing classes. So this is how the object that represents a class actually gets initialized when that class is first brought into the program. And so the first thing to know is that a class is initialized when a symbol in the class is first used, okay, not when the class is loaded, all right? So if you reference any symbol in the class, at the first time that happens, that will cause the class to be initialized. And the reason for doing this is that if you're going to have an error in class initialization, this will cause that error to happen in a predictable place. So if you have an error and you run you have an error in class initialization, if you run the program 5 times, that error will probably happen in the same place every time. So it'll be repeatable and predictable where the error occurs. If instead we had the error happen where you loaded the class at the time that you loaded the class, well, the class might be loaded at lots of different times, so this error here, the error in the initialization of the class, would become non-deterministic if we didn't delay the initialization until some deterministic point in the execution. So now I'll discuss the procedure for initializing class objects in Java. And the first thing I should stress is that this idea of a class object is something that Java has that Cool does not have. I mentioned this on the previous slide, but just to be completely clear, what is a class object? A class object is just what it sounds like. It is the object for a class. It represents a class. Okay, and this is not an instance of the class. This is an object which is the class. Okay, so this is an object which is the class and has all the information about the class. So, it tells you what the type of the class is, what the fields of the class are, and everything else. So this is used for introspection or reflection, and it's necessary in Java because of features like dynamic loading. So if you dynamically load a class and then you want to be able to use that class, you have to have some way of querying what kinds of methods and things the class has, and that is what the class object is for. So there's one class object for each class in Java. All right, so when you load a class, the first thing you have to do is to initialize the class object. And how is that done? Well, we lock the class object for the class. All right, and if that object is already locked by another thread, then we'll simply wait on the lock. Okay, so we will wait until somebody tells us that it's okay to proceed. Now, once we obtain the lock on the class, we have to do a check to see if the class is already being initialized. All right. So, and it could turn out that it is our thread. It is the same thread is already initializing the class. And how could that happen? Well, remember that a class can have fields of the same type. So I could have a class called X, and then it could have a field of type X in it. And the way classes are going to be initialized is we're going to have to initialize the class itself, and then we're going to do that by recursively initializing the classes for all the fields, or at least making sure that the classes for all the fields are initialized. And if we have a recursive structure here with the same class mentioned in a field as the name of the enclosing class, then we will get this situation where the thread initializing the class may attempt to initialize the same class again. So if we discover that we're already initializing this class, we simply release the lock and return. Now, another possibility is that the class is already initialized. So if when we finally get the lock, we discover that some other thread got in there and initialized the class before we had a chance to, well, then there's nothing to do and we just return normally. All right. Now, if neither one of these things is true, okay, if we get the lock and we discover that the class is not already initialized and that we're not already in the process of initializing the class, then we will mark the class to note that initialization is in progress by this thread. Okay, so we'll indicate that the class is being initialized and that we're initializing it, and then we'll unlock the class. All right, the next thing that happens is we'll have to initialize the superclass, and that will mean and then we'll initialize all the fields in textual order. But because Java has what are called static and final fields, we will initialize those first. Okay, so static final fields will get initialized before any other fields in textual order. And of course, we'll have to give every field a default value before initialization, just as in Cool. So this step 5, is very similar to what goes on in Cool. Now, if there's an error during initialization, so some part of the initialization throws an exception, then we're going to mark the class as erroneous. Okay, we're going to mark this class as no good and can't be used, and that's the best that we can do. So if there's an exception during initialization, we just have to give up on that class, and so it gets a special mark on it saying that it's erroneous. And if there are no errors, if we succeed in initializing the class and without any errors, then we're going to lock the class again. We will label the class as initialized, all right, and then we'll notify the threads that are waiting on the class object. So anybody who is blocked waiting on the class object will now be alerted that the object is ready, and then we'll unlock the class. Okay, and so that's a rough outline of how class initialization in Java works. I skipped over a few things and oversimplified a bit. So this isn't the complete description, but these are the main points, and they illustrate how the various features of the language have to interact. So you have to worry about concurrency, you have to worry about exceptions, you have to worry about static and final fields, you have to worry about inheritance. I mean, all these things have to be dealt with together in the design of a single algorithm to do class initialization. Stepping back for a moment, this discussion of class initialization in Java illustrates a general point about designing complex systems. So in any system with a certain number of features, and every system is going to have some number of features, let's call it n, because you want to provide some functionality. Obviously, there are things the system is supposed to do, so it's going to have some features to do those things. But as you add features, you get lots of interactions, potential interactions between the features. And if we think about even just the pairwise interactions, if I have n features, then I'll have about n squared pairwise feature interactions. And the point there, of course, is that as I add features, the number of possible interactions grows superlinearly in the number of features. I mean, it grows much more quickly than the number of features. And so adding the next feature, you have to consider all the previous features that you already have in the system and how this new feature affects them. And this is why it becomes very difficult to extend or build systems that have a lot of features. All right? And this is just the pairwise features. This is just considering pairwise interactions between one feature and another. If I have to start worrying about subsets of features and thinking about how all possible subsets of features might interact with each other, well, then this number of potential interactions will grow not just, it will grow, in fact, exponentially. So it'd be way more than quadratic. And the bottom line here is that big featureful systems are hard to understand. This is a general lesson in computer science in any kind of discipline that wants to design complex systems. And this lesson applies to programming languages. It applies to every other kind of software system that you might want to build. But somehow it has a particular force in programming languages because these interactions between the features, these are the features of the programming language, they happen at a very fine grain. And these things can be composed arbitrarily. And so you really do have to work out in language design what all the interactions are in order to have a language that programmers can actually understand and use productively. All right, and that really, I think, is the big idea one of the big ideas that we've talked about throughout the course. And I hope one of the things that you would take away from this lecture, at least in particular. So to summarize and conclude our discussion of Java, I think Java is a well-done language. By production standards, it's extremely well done. So it's one of the best designed and best specified languages that's in use today. It brought several important ideas into the mainstream. So when it was new, it brought ideas that had been around for a long time, but had not found their way into a production language that was very, very widely used. And in particular, Java was the first language to be very widely used in commercial settings that had strong static typings, that had real guarantees that were provided by the type system, and also that was a managed language that had a garbage collected memory. But that doesn't mean it's perfect, and Java also includes some features that at the time that it was designed that we didn't really fully understand, and I would say that these are probably the areas where there's still some roughness in the Java design. So things like the way the memory semantics work in the presence of concurrency, probably still has, most people would agree, I think, has some problems and some little gray areas that as a programmer you probably want to stay out of. And the other thing is that Java just has a lot of features. And as I said before, when you have a lot of features, you're going to have even more feature interactions, and that leads to complexity that becomes difficult to manage.